Hello everyone, welcome back to my channel. So this is my sixth video of my first playlist of theory of computation. In this video, we are going to solve question number 6 of and Sem exam of theory of computation. So here we go. Firstly, let me introduce myself. Myself Saloni Chauthani, currently pursuing Master of Computer Applications from International Institute of Professional Studies, DAVV, Indore. In this video, we are going to solve question number 6 of and Sem exam of theory of computation. So let's see what the question is. The question is, give two examples of each of the following. In this question, we have given some problems and we have to give example for each of the following. The problems are first decision problem, another one is optimization problem, another one is undecidability, another one is P and NP, another one is NP and NPC, and another one is recursive language. So let's see first for decision problem. Decision problem are problems for which the answer is either yes or no. Here are two examples of decision problems. So the problems are first halting problem. Given a description of a Turing machine M and an input string W, does M halt on input W? In other words, is there a finite sequence of steps that M can take that will eventually lead it to the entering a halting state when given W as input? This problem is famously undecidable, meaning that there is no algorithm that can always correctly determine whether a given Turing machine halts on the given input. The second one is graph reachability. Given a directed graph G and two vertices S and T, is there a path from S to T in G? This problem is also known as the reachability problem. It's decidable and can be solved using algorithms like DFS, depth first search, and BFS, breadth first search. However, it's a fundamental problem in graph theory and serves as the basis for more complex graph algorithm and problem. Now, let's see the another one. The second one is optimization problem. Optimization problem involve finding the best solution, maximizing or minimizing from a set of feasible solution according to some objective function or criteria. Here are two examples of optimization problem. The first one is traveling salesman problem, TSP. Given a list of cities and the distance between each pair of cities, the goal is to find the shortest possible route that visits each city exactly once and return to the original city. This problem is NP-hard, meaning that no known polynomial time algorithm can solve all instances of the problem efficiently. However, there are approximation algorithms and heuristics that can find near optimal solution. The another problem is knapsack problem. Given a set of items, each with a weight and a value and a knapsack with a maximum weight capacity, the goal is to maximize the total value of items that can be included in the knapsack without exceeding its capacity. This problem comes in two variants. The 0-1 knapsack problem, where items cannot be divided, and the fractional knapsack problem, where items can be divided. Both variants have efficient dynamic programming algorithm to find the optimal solution. The another one is undecidability. So, undecidability in theoretical computer science refers to problem for which no algorithm can exist that always correctly determine whether a given instance of the problem has a solution. Here are two examples of undecidable problem. So, the first one is halting problem. Given a description of a Turing machine M and an input string W, the halting problem asks whether M halts, completes its computation on input W, or if it enters an infinite loop. Alan Turing proved in the 1930s that the halting problem is undecidable, meaning that there cannot exist a general algorithm that correctly decides whether any given Turing machine halts on given input. The next one is post correspondence problem, PCP. In the post correspondence problem, given a finite set of tiles, each with two strings written on them, the question is whether there exists a sequence of these tiles such that concatenating the corresponding strings on the tiles from the sequence results in two identical strings. Emil Post introduced this problem in 1946 and proved its undecidability. It's one of the classic examples of an undecidable problem in theoretical computer science. The next one is P and NP problem. Certainly, P and NP are complexity classes that classify decision problem based on the efficiency of their solution. Here are two examples of problems in each class. P, polynomial time. The first one is sorting. Given a list of elements, the problem is to arrange them in ascending or descending order. Efficient algorithms such as merge sort, quick sort, and heap sort can solve this problem in omega n log n time, where n is the number of elements in the list. Sorting is a classic example of a problem that belongs to the complexity class P because it can be solved in polynomial time. Now, the another problem is shortest path. Given a weighted graph G and two vertices S and T, the problem is to find the shortest path from S to T in G. Dijkstra algorithm and Bellman-Ford algorithm are examples of efficient algorithm that can solve this problem in polynomial time. Both algorithms have a time complexity of omega mod of v square plus mod of e, where mod of v is the number of vertices and mod of e is the number of edges in the graph. Therefore, the shortest path problem is in the complexity class P. Now, the another problem is NP, that is non-deterministic polynomial time. The first problem in this is traveling salesman problem, TSP. The TSP is a classic optimization problem where a salesman must visit a set of cities each exactly once and return to the starting city, minimizing the total distance traveled, while verifying whether a given tour is a solution to the TCP can be done in polynomial time. Finding the optimal tool is believed to be a difficult problem. The decision version of the TSP, which asks whether there exists a tool of length of most k, is in the NP class because a proposed solution can be verified in polynomial time, but finding the solution itself efficiently remains an open problem. The another one is Boolean satisfiability problem, SAT. In SAT, the goal is to determine whether a given Boolean formula can be satisfied by assigning truth values to its variables. For example, given a formula in conjunctive normal form CNF, the problem is to find an assignment of truth values to variable that makes the formula evaluate to true, while verifying the proposed solution to SAT can be done in polynomial time by checking if it satisfies the formula. Finding such a satisfying assignment efficiently for all instances of SAT is conjectured to be NP complete, meaning that it is one of the hardest problems in NP. That's all for this video. Thank you so much for watching my video. If you really like this, do comment on my video and do subscribe to my channel. Thank you for watching.